When does my program do this? Learning circumstances of software behavior. My name is Alexander Kampmann and I'm from the CISPA Helmholtz Center for Information Security. Today I present Alhazen. Let me illustrate Alhazen with an example. Let's say you have a calculator program. The calculator fails on square root of minus 900 and behaves as expected on tangent of 9. Obviously, you would want to know why. Alhazen uses a context-free grammar to analyze the inputs and generates a model which explains why the failure occurs. In our example, the model would tell you that the program fails if x in square root of x is smaller than 0. You can use this model to filter bug-triggering inputs, generate more tests, or limit scope in debugging. Alhazen builds those models from features that we extract from each of our example inputs. We put those features into a decision tree learner, and the learner generates an initial hypothesis on why the program fails. In this case, the hypothesis indicates that the program fails if the maximum number is smaller or equals minus 445.5. This is not correct. The number needs to be smaller than 0, and also the function needs to be square root. However, we can use this hypothesis to generate more inputs, say cosine of minus 446.5 and cosine of minus 444.5. We can then put those inputs into the program under test and observe that both of them pass. We extract features from the new inputs and feed those into the decision tree learner in addition to the features from the inputs we already had. This allows the decision tree learner to generate a more precise hypothesis, which already contains the fact that the function needs to be square root. However, the bound on the number is still wrong. After repeating this process for several iterations, the tree finally comes up with the correct hypothesis. Alhazen combines the decision tree learner and the test generator into a feedback loop to generate a model of program behavior, which can be used to filter bug-triggering inputs, generate more tests, and limit scope in debugging. Let's have a look at the input features we are using in Alhazen. We derive those input features from a context-free grammar that describes the program input. This is the grammar that we are using for our example. The grammar derives a string that consists of a function name, a parenthesis, and a number, followed by another parenthesis. Possible function names are square root, tangent, sine, and cosine. A number is derived of an optional minus sign, one of the digits from 1 to 9, any number of the digits from 0 to 9, followed optionally by a decimal dot, and at least one of the numbers from 0 to 9. We can use this grammar to transform the program input into a so-called derivation tree. For square root of minus 900, the tree looks like this. The start symbol derives function, and function derives square root. On the right-hand side, the start symbol derives number, and number uses several derivation steps to derive minus 900. I've used a triangle to denote that there are several derivation steps below number. We will derive 4 types of input features from this: existence features, length features, maximal codepoint features, and numeric interpretations. But before we determine any features, we do a grammar rewrite. For each subtree of the derivation tree, we introduce its leaf word as a new alternative in the grammar. In this example, for the subtree below number, we introduce the alternative minus 900 for the number production. For the subtree below function, we would introduce the option square root for the function production, but we don't because it already exists. For the entire tree, we introduce the option square root of minus 900 at the start symbol. After this rewrite, the grammar is ambiguous. This means that for the same word, square root of minus 900, I am getting 3 parse trees now. For deriving features, we always look at all possible derivation trees. For the existence feature, we can check which production rules have been used within the derivation trees. In our example, the start rule has been used in all 3 derivation trees. Therefore, the existence feature is set to 1. The start rule derives to square root of minus 900 in the 3rd tree, which means the existence feature is also 1. Function derives square root in the 1st and 2nd tree, so we set the existence feature to 1 again. Function does not derive tangent, sine or cosine in any of the trees, so we count this as non-existing. The number production is used in the 1st and 2nd tree, therefore it is existent. And number derives to minus 900 in the 2nd tree, so this is existent as well. The next feature is the length feature. The length feature expresses the length of a subword below a production rule in characters. In our example, for all 3 trees, the subword below the start symbol is the complete word, and therefore 11 characters. Number always derives minus 900, so the length here is 4. Function always derives square root with a length of 4. However, the production rule function can only derive a predefined set of words. The existence feature already tells us which of those is used, so the length feature would not give any additional information here. Therefore, we don't have a length feature for function. The maximum code point feature expresses the maximum code point in a subtree of a derivation tree. For the start symbol, this is 116, which is the code point for the t in square root. For number, this is 57, which is the digit 9. For function, we do not use this feature. As with the length feature, it would not give any additional information. We also use the numeric interpretation of the leaf word of a subtree of the derivation tree as a feature. In the example, this only works for number, which gives us the value of minus 900. If there were more than one occurrences of number, we would use the maximal numeric interpretation for all those trees. The next building block for Alhazen is how to generate new inputs which exercise the path in the decision tree. The basic algorithm to generate from a grammar is quite simple. You start at the start symbol and traverse the symbol on the right-hand side of the production rule from left to right. In this case, this means we start with the function symbol. Going down in the grammar, we can see that function is one of square root, tangent, sine, and cosine. If we want to fulfill the conditions we got from the decision tree, we need to choose a specific option. We will discuss how to select an option later. For the sake of the example, just assume that we pick square root. Therefore, square root is the beginning of the word we generate, and we also record the decision in a decision list. Then we can go back up into the start symbol and look at the parenthesis next. This parenthesis makes it into the word we are generating, but we do not record anything in the decision list because there's no decision to be made here. The parenthesis has no alternative. Next, we go to the number production. Again, going down in the grammar, we find that a number starts with an optional minus sign. For the sake of the example, let's say we use the minus sign. The minus sign goes into the generated string and the decision list. Next, we generate from the regular expression. This actually needs several decisions. If we want to generate the number 900, this is 4 decisions in total. First, we generate a 9 for the first character range. Then we generate a 0 for the next character range. Then another 0 for the same character range. And then we decide not to go on despite the fact that there is a star. Please note that I'm also recording a decision that does not lead to anything in the generated string. We go on to the optional part of the number production and again generate nothing for the sake of the example. We also record this in the decision list. Then we can go back up to the start symbol and look at the parenthesis, which is the end of the start symbol. Here we again generate a parenthesis, and there is no alternative, so we don't add anything to the decision list. The basic algorithm gives us the leaf node, square root of -900 in this case, and the decision list on the right hand side. Next, we will look at how to make the decision such that we fulfill the conditions laid out by the decision tree. Let's have a closer look at the decision list. This list contains the decisions that we made while generating the parse tree. You can think of this as a tree. In the beginning, we can choose between all the different functions. We decide for the square root function, and now we can decide whether we want the minus sign or not. We decide for the minus sign, and now we can decide between all the different numbers that we can use. This decision taking forms a tree structure, and in a tree we can use a tree search. This means whenever we need to take a decision, we calculate a heuristic value for each option, and then choose the one with the best heuristic value in a greedy process. For calculating the heuristics for the existence feature, we can calculate distance in the decision tree. That is, how many more steps do we need to reach the required symbol. For maximum code point features, we can identify the production which contains the required code point and again use the distance. For numeric interpretations, we can parse the required number and add the generated parse tree as a subtree when we encounter the root production. Length features are a little bit more complicated. Let me illustrate this with an example. In the grammar on the left, I want to have the length of the subword below the start production as 11. In the algorithm, I first look at A, which requires me to generate for this regex. There is a star at the end of this production, indicating that I can use strings of arbitrary length here. For example, those 3. None of them would help me to fulfill the requirement. For the first one, I got 0 characters, but generating B and C only gives 1 and 4 characters respectively, which does not lead to 11 characters in total. For the second one, I get 4 characters, but again that makes only 9 characters in total. The last one has 11 characters on its own, so we overshoot the target when we generate B and C. We would need to generate 6 or 7 characters, but we cannot know that without looking at upcoming decisions, which would violate the idea of using a greedy algorithm. Therefore, length features fail occasionally. There is also another problem which makes this algorithm fail occasionally. This is ambiguity. While generating, we look at one parse tree, the input we are generating only. But due to ambiguity, there may be another interpretation, which may violate one of the conditions. If things went wrong with the greedy search, we will just restart the tree search, this time taking at least one decision differently. In our evaluation, we are using 24 different bugs. 6 are within the Google Closure compiler, 2 in Rhino, a JavaScript interpreter, 1 in Jensen, a Java library for interpreting JSON, 7 in Find, one of the GNU core utils, and 8 in grep, which is a core util just as well. Our first use case is filtering bug triggering inputs, the second one generating more tests, and the third one limiting scope in debugging. The idea for the first use case is to use the model to predict whether an input is going to trigger the bug or not. Imagine a system running on a web server which processes user inputs. If a user sends a bug triggering input, the program fails on the server, causing service disruption or even security problems. Alhazen's model can be deployed as a filter and guard the program against bug triggering inputs until a real fix can be deployed. In our experiments, Alhazen classified 92% of all inputs correctly. While we have high accuracy on all bugs, there is an interesting outlier. In this case, grep creates additional characters in the output. The failure occurs if the encoding is UTF-8, which is done by setting this environment variable. The matching is case insensitive, which is done with the option -i, and the regex matches the input. The last of those conditions, the input matches the regex, is not a feature that Alhazen can recognize. Therefore, it cannot add this to its diagnosis. This shortcoming could be fixed by adding the feature to feature extraction. Even without this adoption, Alhazen classifies 66% of all inputs correctly for this bug. The second use case for Alhazen is to generate more tests. Those tests may help to detect regression bugs. Also, almost all automated bug fixing techniques require an extensive set of tests. On average, 68.5% of all inputs produced by Alhazen as failure-inducing actually trigger the failure. This number even improves if we generate passing and failing inputs. On average, 92.5% of the inputs produced by Alhazen as passing or failing pass or fail respectively. In quite a few cases, we even got a perfect result. In this bug, grep freezes when the encoding is UTF-8, the full string option -f is used, and the pattern is empty. The last condition is not a feature in the original grammar, but our grammar rewrite introduces the empty pattern as an alternative, and therefore as an existence feature, which allows Alhazen to achieve 100% accuracy for bug triggering and benign inputs. After looking at some of the models, we ask ourselves whether they may be useful in debugging. Unfortunately, this is difficult to evaluate. Alhazen does not give a bug location, which could be checked against the location of the fix. Also, it does not minimize an input, which could be checked against the original input. We are currently preparing a user study to evaluate Alhazen's use as a debugging aid. For this work, we look at how much Alhazen prunes the search space in debugging. The information that the bug occurs if x is smaller than 0 in square root of x allows the programmer to look at the square root function and ignore the remainder of the program. In our experiments, the model produced by Alhazen allows programmers to focus on less than 5% of input features. To summarize, Alhazen shows that a decision tree learner and a test generator can be combined into a feedback loop to generate a model of program behavior, which can be used to filter bug triggering inputs, generate more tests, and limit scope in debugging.